What I wanted to do is sort of briefly review the reasons why people use high voltage microscopy. I'm sure you all know why you're here, why you're interested in the high voltage aspects of microscopy. And I suppose for most of you it has to do with the ability to look through thicker specimens than you can look at with a conventional microscope. And indeed, that's probably the primary driving force for the development and application of the microscopes. But for a wide class of other people, the primary influence is the increase in resolution that's obtained with using the higher voltage. And that's probably at least as important an aspect in material science as the ability to look at thicker specimens. But also for a few of us doing biological studies, the increase in resolution that's obtained and easily obtained with a higher voltage is probably going to turn out to be a critical aspect. Now, I had been saying in a lot of talks that the microscope itself was not a limiting problem in our efforts to obtain high-resolution images, because indeed the resolution that we've been able to get with a microscope is well beyond, say, 3.5 angstroms, and has been for quite a few generations of microscopes. But it turns out that essentially everything leads to higher resolution with the higher voltage microscope. And what that means is that it's turning out to be far easier to obtain high resolution data than it was at 100 kV. And what I want to do is sort of review the factors that influence the resolution and kind of give you some background on the importance of different things. And then to go through some of the operational protocols or considerations that one has to keep in mind when you're trying to record data at high resolution from organic specimens that are sensitive to radiation damage. So the background of my work is basically electron crystallography of thin protein crystals. And this is a major shift in gears, I suppose, from the talks you've been hearing before, where essentially the specimens that you've seen on the screen were probably all a micron thick or so, or else were 3D reconstructions from series of sections where the whole reconstruction was several microns thick. Our applications mostly involve specimens that are on the order of 50 angstroms thick, or maybe 100 angstroms thick, primarily specimens that are integral membrane proteins that form crystals in 2 dimensions, essentially in the plane of a membrane, and we look at a membrane patch on the microscope grid. So we're dealing with very thin specimens, and we like to think that our specimens interact in a very simple way with the electron beam, so that the electron is at most scattered once as it goes through the specimen, and that we can essentially ignore inelastic scattering. Now, obviously, inelastic scattering is really the limiting factor in all of microscopy of biological things. That's what gives you the radiation damage. So we can't ignore it, but we suppose that it contributes a small effect to the image contrast. And indeed, that the image contrast is strictly formed by the interference of elastically scattered electrons with the unscattered part of the electron beam. So we're strictly looking at phase contrast imaging and hoping that our linear approximations, where we're looking at single scattering and phase contrast, are valid. So we've been trying to get resolution of biological specimens on the order of 3.5 angstroms, and indeed to do this in 3 dimensions, basically by taking images of our membrane crystals from various orientations, tilted, say, plus or minus 60 degrees, and combining data from these different projections at up to high angle tilts in the computer to build up a model of the electron scattering or the density of the specimen to a resolution that's close to 3.5 angstroms. The goal of 3.5 angstroms was set because it looked like a reasonable resolution goal even at 100 kV. but also with a 3D map at that resolution, then we could take the known amino acid sequence of our protein and fit it to the density map in the way that X-ray crystallographers do, and actually solve structures to atomic resolution. And we actually have done that. The first application was in the determination of the structure of bacteria rhodopsin, which is a project that's been underway for a long time. I suppose everyone here was at least born by the time the original 3D structure of BR was published in 1975. Although a large part of the world's population has come along since then. That's the first time I've really thought of it in that context. But indeed, we managed to get images to give us a density map that has a resolution, at least in one direction, of at least 3.5 angstroms, and in the other direction, enough so that we could determine the position of enough amino acid residues in the density map to fit the rest of the peptide sequence into the model. It's not just from working at a 100 kV that project took over 15 years. There were a lot of other technical details that had to be worked out in the meantime. But my expectation is that although it looks like the next 2 atomic structures will be solved using data just at 100 kV, those will each take sort of on the order of 5 years each to collect data and to process. But the next generation of proteins that are solved in this way, many of them will be using higher voltage microscopes, and the progress will be a lot more rapid. Now, I can't say that they'll be done in a year. Hopefully, they'll be done in less than 5 years. I was talking with David DeRosier at the biophysics meeting, and his vision of the future is where you come in the morning with a specimen and poke it into your microscope and push a few buttons on the computer control, and by the end of the day you have your structure. Now, the world's population will increase a significant amount again by the time that stage is realized. But I guess we ought to move on to the reasons that things are better at high voltage. And I suppose we're going to have the front lights off. And if I turn this up a little bit, probably you'll be able to get that all on the video. Like I say, most everything that has to do with the microscopy is better at high voltage. There are 1 or 2 things that are not, which are really quite significant. But I'll sort of go through the list here and discuss aspects of each of these. So the first items, the contrast transfer function and the coherence envelope functions. These are mathematical concepts that basically describe the intrinsic resolution of the microscope. And what I suppose I would like to do is have the lights on and draw a little picture of the microscope imaging system on the board here. I've already drawn the objective lens, which you can consider to be the whole imaging system of the microscope. So if I draw a specimen here, and in particular, if I draw just a point on the specimen, the electron wave coming through this point will, if this were a real ideal point, the electron wave scattered from the point would be a spherical wave. And in passing through the objective lens, if this were a perfect lens, that spherical wave would be converted into a plane wave. So you'd have a plane wave propagating down from the objective lens. Now, if this specimen is in the front focal plane, and it is approximately in the front focal plane of the objective lens because the lens is run at a fairly high magnification, in the back focal plane where you have the electron diffraction pattern, this plane wave serves as quite a good reference. Now, the actual objective lens is never quite perfect, and as Eileen pointed out, the best images are obtained when you're not exactly in focus. the best phase contrast images. Now the reason that happens has to do with the fact that these scattered waves are shifted in phase by a quarter wavelength with respect to the unscattered waves. Now the only influence of that is that when the interference occurs in the image plane, there's no constructive or destructive interference between the scattered and unscattered electrons, and that generates no contrast in the perfectly focused image. The purpose of the defocus that you use in order to produce phase contrast is to add a little more phase shift so that the unscattered and scattered waves are out of phase exactly by half of a wavelength so that you get destructive interference. That'll generate the image contrast. Now, the defocus that you introduce by changing the strength of the objective lens, you can also, at least in principle, refer to by conceptually moving the specimen from this point to some other point. And in that case, the curvature of these waves will be different when they enter the objective lens, and the result is that coming out of the objective lens, the waves will no longer be plane waves, but they'll be spherical waves with probably some large curvature, but they won't be quite plane waves. And we describe by this difference in position between the spherical wave and the plane wave, that corresponds to a phase shift. And that's the shift that actually produces the image contrast. Now, the other thing about the objective lens is that it's really a crummy lens in the sense of in comparison with an optical lens, at least in the amount of spherical aberration that it produces. Now, the spherical aberration you can look at as producing a phase shift that actually I could draw like this. If this coordinate here we call S, which corresponds to the spacing between details in the image. So this is a spatial frequency. This phase shift here from defocus goes as S squared. This phase shift due to spherical aberration goes as S to the fourth. And it's possible to play these two off against each other, the defocus and the spherical aberration, so that over, if I draw some optical axis in here, over some range you get a phase shift over some good range of spatial frequencies. You get a phase shift that's about the additional quarter wavelength that you need to get the phase contrast imaging with a half wavelength phase shift total. Now, where the voltage comes in has to do with the range of scattering in the back focal plane. At 100 kV, electrons are scattered into wider angles because the wavelength is longer. So if you have spacings in the specimen, suppose at about 3.5 angstroms, you'll have electrons that are scattered out to, say, this range around here in the diffraction pattern. That means out to some range of some resolution that's not as good as 3.5 angstroms, maybe 5 angstroms to 20 angstroms or so. In this region here is where you get good phase contrast imaging. So out to a limit of something around 5 angstroms. At 400 kV instead of 100 kV, the scattering is reduced. The scattering angle is reduced because the wavelengths are much shorter, and these diffracted beams at 3.5 angstroms will come in somewhere in here. And in fact, you can arrange to get this good region of the good phase shift out close to 2 angstroms, at least sort of around 2.5 angstroms. Now, that's a little bit complicated diagram at this point, but I have to make your life worse by putting up an equation or two, just because I come from a physics background, I guess, and I want you all to suffer, right? The equation that describes the contrast as a function of resolution is this top equation here, the contrast transfer function. This is probably familiar to some of you. It's the sine of the wave aberration function, or basically the sine of this total phase shift here, the sum of the defocus and spherical aberration phase shifts, as a function of this coordinate s. It's easier to see that in a plot, and in fact, you don't need to remember the equation as long as you remember some of these plots. This looks backwards from here. It's not backwards at all. On the top here is the situation for the first picture I drew, where you sort of have the proper focus for resolving out to the highest resolution at 100 kV. Now, the focus where you get this wide range of the proper phase shift is known as Schertzer focus. It's not the focus that most of you would choose to use for imaging large structures, because it doesn't produce good phase contrast for large features in the image. But for when we're trying to get resolutions on the range of 3 to 5 angstroms, it's normally the optimal focus. The horizontal axis here is the resolution. This goes from very large spacings to spacings that get smaller as you go farther out here. The limit in these plots is about 2 angstroms. So what you see here is that somewhere around 3.5 or 4 or 5 angstroms, the dark curve goes through 0. Now, the sine function is this curve that wanders back up and down between the plus and minus 1 limits here. And as you see, as you go to higher resolution, the oscillations in that function become more and more rapid. Basically, what this means is that at high resolution, the contrast becomes too complicated to interpret easily. It's not impossible to interpret, but it's far too complicated to interpret just by looking at a micrograph. And so one normally sort of truncates the resolution in the visual interpretation of the image at about the first 0 in this sine function. If you go from 100 kV to 400 kV, the shape of this thing basically extends way out towards higher resolution, and this range where there are no oscillations in the contrast transfer function extends close to 2 angstroms. These are parameters that are not too far different from our JUL 100B that runs at 100 kV and the JUL 4000 running at 400 kV. Now, this part of the curve in here is probably what's more interesting to most of the people here, where you're looking at objects that may be on the size of 10 or 100 angstroms or even larger. The fact that the curves in both cases are very close to 0 means that those very large spacings have very low contrast in the image. I think it was Eileen mentioned images taken at 20 microns under focus. This is the kind of defocus that's required to get resolution or good contrast at very low spatial frequencies or very large objects. We, from time to time, end up taking pictures at about 1 micron under focus, and the effect of high voltage here is again to stretch out these oscillations so that within the resolution range of interest there are fewer oscillations in the sine function, which is good in one sense. Aside from extending the range at which the first 0 in this function happens to higher resolution, when we finally get into processing our images in the computer, we compensate for these oscillations in the transfer function. And with far fewer oscillations at high voltage, it makes life not just easier, but there's a limit to how many of these oscillations we can deal with or how close they can be spaced. And so even with the higher defocus values, we can actually extend the resolution to much higher values with the 400 kV. Now, the second item on the list here was the coherence envelope functions. Again, you don't have to write down the equations. You don't even have to remember them. But basically, these are two functions that cause the resolution itself not to be limited, but cause the contrast to decrease as you go to higher resolution. These are really the functions that limit the resolution, at least for the high-resolution imaging regime. And probably the extension of these two envelope functions with the higher voltage microscopes is the effect that really provides increased resolution. The spatial coherence envelope has to do basically with, or arises from the fact that the electrons come into the specimen from essentially different angles. Now, I suspect that you all know that as you increase the size of the condenser aperture, of course you get a brighter electron image on the fluorescent screen, but as you go out of focus, the image gets fuzzier faster. If you decrease the condenser aperture size, you can go farther out of focus and still retain a fairly sharp image. And that's precisely the effect of the spatial coherence envelope function. Alpha here is the size of the condenser aperture. The delta Z is the defocus, and S again is the coordinate of the resolution. These are both of the envelope functions are simple exponentials, so as the argument in the exponent gets larger, the value of the exponential gets smaller, and the contrast goes to 0. So the smaller alpha is, the smaller this value here is, and the larger S can be to give you the same contrast. The temporal coherence has to do with essentially variations in focus of the image. Now, if you picture varying the objective lens, of course, the image will change focus. If you picture varying the high voltage, the image will also change focus. And the temporal coherence envelope function can be thought of as a function that incorporates all of the effects that cause the focus to vary. And this little delta here is basically a parameter that reflects the width of the focus variations during the time that you're taking the image. Now, so that includes instabilities in the objective lens current and instabilities in the high voltage. Now, those two instabilities in the most modern microscopes are probably quite small compared to the effective defocus range caused by the energy spread in the electron beam. And what this means is that not all of the electrons coming off of the filament have precisely the same energy. There's a certain energy spread, which is given by some well-known distribution, and it's characteristic of any particular type of filament or electron source. Now, the energy spread for a typical tungsten filament is something on the order of 2 volts. If you use a field emission gun, in principle, you can get the energy spread down to a few tenths of a volt. With the lanthanum hexaboride gun that is used in most of the 400 kV microscopes, the energy spread is somewhat less than the 2 volts for the tungsten gun. But basically, this is sort of the number that sets the lower limit to this delta. So in both of these envelope functions, there are parameters that do not depend on the wavelength, but both of them have factors of the wavelength in the exponential. So as the wavelength is decreased, these exponents in each case decrease, and so the contrast retains good value to higher resolution. That's reflected in these curves also. These envelope curves here, this and say this here, are the essentially product of the coherence envelope functions, both for spatial coherence and temporal coherence. And you can see that indeed the envelope functions go to higher resolution before they fall close to 0. So this is probably one of the most direct influences of going to high voltage on the resolution. But in fact, that's not nearly the only thing. Both of those have other implications, and one of the more significant ones has to do with the depth of focus. Basically, if we look back to this image, this picture here, the fact, well, let me just point out that the defocus in these bottom plots is about 1 micron. Okay, so in the top plots, the defocus is close to Scherzer focus for either 100 or 400 kV. In the bottom plots, the defocus is about 1 micron. Now, the bottom line here is that these oscillations occur much more slowly at high voltage than they do at low voltage. What that means is that you can change the focus more without changing the position of these the sine function at high voltage. So that has two aspects. One has to do with how much vibration of the stage you can deal with. Inevitably, I believe that the grid in the microscope undergoes a certain amount of vertical motion. How much motion is an open question, but there probably are cases where that's a real limitation, particularly in the case of cold stages where there's not only a little bit less mechanical rigidity than the normal stage, but there's also out on the end of a specimen exchange rod sitting in some position that really looks quite precarious. There's a dewar full of liquid nitrogen that, if it's not performing right, will be bubbling away, or at least is somewhat subject to mechanical vibrations. And it's quite clear that in the case of our cold stages, the specimen is indeed bouncing up and down in some acoustically excited manner. But that's not so bad at high voltage. I mean, that happens either with a 100 kV or a 400 kV cold stage, but we can tolerate almost 4 times as much motion with the high voltage microscope. And that's very fortunate, because this is the problem with the vibration is one that is not obvious how we're going to solve in the real near future. As we tilt our specimens, there's 2 things that happen. One, this vibration perpendicular to the plane of the grid actually still occurs, and it's with the tilted specimens that we have the strongest evidence for that motion, and also where it gives us the most problem. Now, if you're looking down on something that's moving up and down, you're really not sensitive to that motion. But if you're looking at something that's tilted like this, let me get something that shows up a little better. So if you have an object tilted like this that's moving in this direction here, that's really going to smear out the resolution in the direction perpendicular to the tilt axis. And that's precisely what we see with tilted specimens, that we have quite a difficult time getting good resolution in the direction perpendicular to the tilt axis. Now, that's not, unfortunately, a problem that's better with the high voltage microscope. It's not worse, but at least it's not yet solved. That's something that we'll have to solve with some improvements to the cold stage perhaps, or better specimen support, that, some sort of mechanical stiffening of the grid that reduces the vibration. Because we do have to work with the tilted specimens. In order to get the three-dimensional reconstructions, we have to be able to look at specimens at different tilt angles. And indeed, we like to work with specimens that tilted up to at least 60 degrees. Now, what happens when you have a specimen tilted at that high an angle is that one end of the film is going to be way over-focused and one end is going to be way under-focused. And if you have a transfer function that varies from something like this at one end through something like this in the middle to something again that looks like this at the other end, that becomes computationally quite difficult, and under many circumstances it means that the resolution will be not nearly as good in practice at the two ends of the film. So with the increase in depth of focus with the high voltage microscope, essentially we'll be able to use a much wider range of the film that's reasonably close to focus. Okay, so the effect of inelastic scattering, as Lee Peachy noted, is significantly reduced at higher voltage. And that's a significant advantage of high voltage microscopy. What that means is that radiation damage occurs more slowly at high voltage. Now, the downside of that is that the scattering of the elastic scattering also decreases as you go to high voltage. What that means is that your image contrast decreases. So I suspect you're all familiar with the effect that or those who've worked with a high voltage microscope know that the image contrast is lower. And that's a significant disadvantage, but it's one that we can live with and actually compensate for. The return upside of all of this is that the ratio of elastic to inelastic scattering improves a small amount as you go to higher voltage. So the inelastic scattering drops off by, I guess, about a factor of 2. The elastic scattering that leads to the image contrast that you want doesn't fall off quite so much. So you're causing less damage to the specimen, but because the elastic scattering is lower, it ends up that you have to give the specimen more of a radiation or more electron exposure to get a statistically well-defined image. So in order to compensate for the loss of contrast, you have to use a higher exposure. But the ratio of signal to damage does increase a little bit as you go to higher voltage. Now, the exposure of the photographic film basically is an inelastic scattering event in the photographic emulsion. So the electron comes into the film emulsion and scatters around inelastically, losing electrons or losing energy as it scatters around in order to cause photographic grains to be developable. Because the inelastic scattering is decreased, that means not as many grains will be developed for a given exposure when you're using high voltage. That means the photographic film, on the one hand, needs a little bit higher exposure in order to get the same optical density. But it turns out also that there's an upside to this too, that as the electrons scatter around inside the emulsion, the region in which they scatter and the region which is developed for each primary electron sort of grows as the electron gets down into the film. Let me again just draw a little sort of classical picture of what's happening here. If this is the surface of the photographic emulsion, so that this down below here is the film itself, an electron coming in here will will come in and start scattering around, and either the electron itself or secondary electrons or X-rays generated in the process will cause a region that's sort of a teardrop shape to be exposed and to develop for each primary electron. Now, if the electron has a higher energy, that means two things happen. One is the shape of this teardrop changes to something like this here. And the other is that the narrow region of this may actually extend through and out the other side of the emulsion that contains the silver halide grains. So if this is the extent of the emulsion in the film, at 100 kV, you'll be exposing a region that's something like this here. At 400 kV, the region, the way I've got it drawn here, would look something like this. What this means is that each electron will produce an image that's much narrower on the photographic film. Even though the image won't be as dark, it'll be a lot better defined. And years ago, I measured what amounts to the actual spreading of this in photographic films. We measured it in terms of modulation transfer functions, which is a representation of how good the contrast is at each spatial frequency. And these are data for various films at 100 kV. And the scale of these, the curves go out to spacings of 10 microns on the film. So these are 10 microns per line pair, per dark light line pair. And what you see is that for, say, this was the 4463, which is now the SO163 Kodak emulsion. At a spacing that's somewhere around here, the contrast of the film is down to about 50% of the contrast that it should have on an ideal film. So if the electrons came only straight into the emulsion and didn't spread out in the process of exposing the film, this line would be horizontal all the way across. But as you get to smaller and smaller spacings, these overlap regions, or the spreading regions overlap and the contrast is reduced to about 50% at a spacing that's somewhere around 25 microns on the film. Now, we've made some preliminary measurements at 400 kV, and I expect my pen's not going to draw, but it looks like, has anybody got a permanent pen? Indeed, the results are dramatically improved at 400 kV. Thank you. It looks like with the Kodak film, the MTF is going to look something like this here. That's roughly a factor of 2 improvement at very fine spacings on the film. This AGFA film is one that we've taken to using for the high-resolution work at 100 kV. And within the noise limits of the measurements, at 400 kV, the MTF looks like this. There's very little fall off in the contrast as you go to finer and finer spacings. What that means is that you can take pictures at minuscule magnifications and resolve all the details you'd ever want to see. There are some practical problems with some microscopes that the microscope itself, probably because it's sensitive to magnetic field disturbance, does not perform well at low magnification. And I asked Mike Krisker of JEOL if he could, on a trip to Japan last year, take some images of gold film at 400 kV at about 50,000 magnification. And he did that for me, and he sent some images back. And this is a optical transform of one of his images. What you see here are rings that arise from the oscillations of that sine function in the contrast transfer. But also out here, you see spots that arise from the diffraction from the gold lattice recorded on the image. So this is a 2.3 angstrom lattice image recorded at 50,000 magnification. Now, I was surprised at that, frankly, although I should not have been, because at 100 kV, I once, just for the fun of it, recorded the 3.5 angstrom graphite lattice at 20,000 mag. So I know I can do it 3.5 angstroms at 20,000. Shouldn't be a problem of doing 2 angstroms at 50,000. In fact, at 400 kV, I'm sure that you could resolve 2 angstrom spacings at 10,000 magnification on the AGFA film. That's not a practical thing to do, though, because when you look at the image, the electron exposure is so low that the lattice lines are extremely noisy. There just are not enough electrons to expose the image to a level that's well defined. And this is one thing that we'll probably come back to shortly here. But still, back to these things that are better at high voltage. The physics of the electron gun is such that the gun brightness increases as you go to higher voltage. The hand-waving way to think of that is that you have a filament that's emitting electrons at a high voltage. More of the electrons are pulled straight down into the condenser lens system, or into the first aperture. At 100 kV, they're spread out more. At 400 kV, they're pulled more in the forward direction. So more of the electrons are going in the right direction, or the cone of illumination is smaller, basically. So the brightness is sort of a combination or a product of the coherence and the intensity. And indeed, it's the coherence that is easy to take advantage of. It's easier to use a smaller condenser aperture to get good coherence at high voltage. Now, the intensity increase is actually a little bit offset in practice, because you end up looking through an inch or two of lead glass at the fluorescent screen, which cuts down a little bit on the ease that you can see the screen with. And there is the same problem of shielding with a TV camera. So the increase in gun brightness helps a lot in recording images, although not as much as I had expected in looking at the image on the fluorescent screen. And indeed, the effect of the electrons illuminating the fluorescent screen is similar to the effect of the electrons exposing the film. A given thickness fluorescent screen will, if it's optimized for 100 kV, will not be thick enough to absorb all the electrons at 400 kV, and so will not give as bright an image. If it's made thicker so that you use all the energy in the electron beams, turning that all into light, then the resolution may not be as good, because the resolution in general is fairly comparable to the screen thickness. Okay, now there are a couple of other effects. The misalignment of the electron beam causes a distortion of the image that has not been widely considered in high-resolution studies, although it's one of the things that we absolutely have to deal with in combining high-resolution images of crystals, because the misalignment causes a phase shift which essentially invalidates the data at high resolution, unless we can determine the beam tilt and compensate for that phase shift. Now, again, because of the higher voltage, the sensitivity of that phase shift is a little bit lower, and that should make processing of the data that we get significantly easier. I mentioned at the beginning that we like to think of all of the interactions with the electron beam and the specimen being simple single scattering. And at 100 kV, there's some evidence that that approximation sort of starts to break down. That, again, is an approximation that's much better at 400 kV. Since the scattering cross-sections are lower, the single scattering approximations are correspondingly much better. One thing dear to my heart is the diffraction-limited spot size. Again, this is a reflection of the increase in gun brightness, or the increased coherence. You can focus the beam to a smaller spot with a given condenser aperture with a given illumination angle on the specimen, at high voltage you can get to a smaller spot size. And this is something that will be useful in spot scan imaging, which is one of the things that I've been doing a lot of. This is a spot scan image, just so you know what I'm talking about, where the beam is focused down to a spot that's around 1,000 angstrom diameter. Of course, it's easy to get a smaller spot than that, but this is still under conditions where we're getting good phase contrast imaging. So the illumination angle, this is actually done with a condenser aperture of about 30 or probably 50 micron diameter. So it's a fairly small condenser aperture. So it's a coherent beam focused into a fairly small spot. Now, at 400 kV, we can focus down to a much smaller spot than this. The reason to do spot scan imaging to begin with is to reduce problems that are caused when the electron beam shines on the specimen. All this electron beam damage we're causing to the specimen causes the specimen to probably go through some kind of a motion like this. Something like a flag waving in the breeze, as the beam causes damage sites at different positions, and bonds are changing and breaking, and interatomic spaces, distances are changing. If the illumination, instead of covering a whole, say, micron or 2 micron area, is focused down to something like 1,000 angstrom spot, the motion of the specimen is markedly reduced. Now, this motion, if the specimen is illuminated over wide angles, actually causes a tremendous loss in contrast at high resolution, or a loss in resolution. With the spot scan imaging illuminating just a small spot at a given time, that motion is decreased tremendously, and the contrast at high resolution is much improved. Now, I'd meant to leave lots of time for questions, but I've probably run so much over that I may as well stop here, and hope that there's time during the demonstrations this afternoon to ask questions related to the mechanics of obtaining high resolution. Thank you.